So the recording is going. Y'all have probably noticed from all my old classes that I do video record all of my classes. So I think for legal reasons, I think I actually have to announce, this is a recording and, you have been recorded. I don't think the mic will pick up casual conversation. But if you, ask a question in a loud voice, especially if you're in the front of the room, you might actually show up on the tape. So, FYI. Okay, so I believe most of y'all, hopefully all, possibly only most, have received an email from me last week with welcome and an email link to the class website, etc. I was told in my earlier class, at least a couple of students did not receive this email. One of them came and we sat down and we worked on it and figured it out. It had gone to his junk folder. If you have not received the email, you may have, and it may be in your junk or spam or trash or whatever, however you do that. So anyway, make sure you got that email from me, and if you are not sure what to be looking for, on the class website, scroll down to the bottom, early announcements. All of my announcements that I make early in the semester, I put on this web page to document, because some people will add the class later, and I want them to know what it is that I've announced. So anyway, there it is. If somehow you legitimately, in fact, did not get the email, there it is. Okay. All right. So let's see here. So y'all have already heard me talk for an hour or more on that recording. Unless you watch at 1.5 speed on YouTube, which is a pretty good way to go. You can get it done in 40 minutes flat, right? Pretty awesome. Anyway, y'all heard me discuss this at length. I'm not going to repeat all of that. The reason I have that recording that I put out at the start of every semester is because all that stuff is really important. It's super important. And I just don't have time in class to talk through all of that, of course. There are a couple of things that I think are so important that not only are they heavily represented on the websites, not only are they discussed at length in the recording, but I am also going to repeat them here in class, in person. This is one of the really big points, right? Now, y'all heard me talk about this, but this is a course about ideas and reasoning, right? Please don't misunderstand what we're doing here, what our goals are here, right? If you come into the exams and you know all the formulas, character for character. Okay, well, that's a little something, but it's probably not going to do it, right? I mean, this is a class about understanding the ideas behind the formulas and being able to, having enough intuition for those ideas and that understanding to be able to use those in creative, practical applications, right? So, anyway, super duper important. What are we here for? What are we trying to do? That's what it is. Okay. And then secondly, also, again, just bonkers important, is this point right here. We just do not have enough time in class to expect in any reasonable way that I would acknowledge that we could do all of our learning in class, right? Now, I understand a lot of math classes are set up this way, especially like, high school and previous, that you come to class, that's where you learn the material, and then, you go home and they make you do some homework, and that's just to kind of build muscle memory, that kind of thing, whatever. There's nothing particularly, there's no learning particularly happening, maybe just, practice, just, speeding up your execution or something like that. So, it's nice, right? If your class time to course content ratio is high enough, then you can do that. But our course content is enormous, right? It's a lot. And, we have the same 150 minutes a week as every other class. So I don't think it's at all realistic. So anyway, make sure, again, a lot to say about this, and it's all in the recording, and it's all discussed at length on the websites. But just be advised and make sure that you're clear. It is expected and assumed that you will be doing lots of learning type study. Again, not just practice, right? But, learning of ideas and this sort of thing outside of class. It just can't be done without that, I think. Okay. And even if it's possible, it's certainly, you're not going to get as good of an experience without, scheduling, making sure you have time to learn outside of class. Okay, so those are the 2 big points. Lots more to say. Before I get into the lecture, though, let me just open up the floor, see if anybody has any questions about any of this administrative or organizational kind of stuff. Anybody? Okay. All right. Good. Let's do some math. This is my lecture notes, which again is y'all can download this. You can have exactly this file that I'll be working off of. Again, I know I talked about this previously, but I think it's a really great way to learn is to have a copy of this on your tablet or computer or what have you, and therefore you see exactly what it is that you don't need to write down because it's already there, right? And then maybe you just annotate with little thoughts, reminders to yourself or what have you. I hope that'll save you writing time, but more to the point, to allow you to do more listening and more concentrating and thinking and digesting, and therefore I think getting more out of the lecture. It's just an opinion. Okay, so why are we here? Why are you taking multivariable calculus, aside from the fact that your major requires it? Said differently, why does your major require that you take this course? What is so great, anyway, about multivariable calculus? So I think this deserves an answer, right? Should know what we're doing here. I hope you're already bought in on this idea, single variable calculus, right? Y'all seen a million examples of applications of single variable calculus in your Calc 1, Calc 2 classes. It's about derivatives and integrals. Derivatives talk about how things change. Lots of things change. The world's full of change. Hardly anything stays the same, right? So, talking about how things change and being able to quantify that, it boggles the mind how valuable that, how many different ways that applies and how many different circumstances. Okay. It's a little harder to talk about integrals and why they're so important. This is I think, commonly misunderstood thing. A lot of people think integrals are for the purpose of computing the area under a graph. I don't think that's at all what integrals are for. And frankly, it's not even a particularly important application. Right? It's a visualization tool. I guess there's something to be said for that. I kind of like it for that reason. Don't get me wrong. I'm not opposed to that point of view. Right? But it's really not why people in most cases want to compute integrals. Right? Ultimately, why are we computing this integral is usually some physics problem, that we're trying to compute an amount of work or an amount of energy or an amount of whatever, some physicsy stuff. Or if you're doing economics, then you're computing some economic quantity, right? And usually it's not actually area. There's some rare circumstances where, you're charged with painting the side of a weird-shaped wall, and you need to know the area so you know how many cans of paint to buy. This is pretty rare, right? So what is it that integrals are for? And I like to say it as to compute what I like to call accumulating quantities. And I'm trying to be as general as possible here. Accumulating quantities, any quantity where the whole is the sum of the parts. Again, pretty broad category, right? If you want to compute the amount of mass in some lump of mass, well, mass has this feature. You chop it up in a bunch of little pieces, the whole mass is the sum of the little pieces of mass. Right? So I'm going to put forth that integrals can compute any accumulating quantity in suitably interpreted. So again, a big category of applications. Okay. All right. By the way, if you're not 100% clear on your understanding of derivatives and integrals, I'm going to point you to my YouTube channel. I have a what do they call it? Playlist, I guess is their word for folder, right? Called Miscellaneous Topics. And I think each one of these is like 15 or 20 minutes or something like that. One of them is called What is a Derivative? Another one is called What is an Integral? And in the let's not talk about how many years I've been teaching multivariable calculus. I've identified various misunderstandings and weaknesses, etc., common weaknesses that some students have with their Calc 2 understanding. And if you think that might conceivably be you, I would encourage you to watch those recordings. Okay. All right. Okay, so that's single variable. Here's the thing. We live in a three-dimensional world, not a one-dimensional world. Sure would be boring if we lived in a one-dimensional world. Right? So we have a three-dimensional world, and here's some kind of, I'm going to say, three-dimensional versions of problems that we've already kind of talked about. So y'all understand the idea of how fast one variable changes with respect to one other variable. Well, here's the thing. Let's talk about temperature in the room. Let's say this room. Why not? Over there by that window where the sun's coming in, I'll bet it's a little warmer. And down here in this corner where there's no sun and it's, down low, etc., it's probably a little cooler. So temperature depends on location. That's what a function is. Right? X, Y, and Z are the inputs that describe where we want to talk about. Temperature as measured at that location is what comes out of that function. Right? You give me X, Y, and Z, I give you temperature. Does that make sense to everybody? Okay, fine. So here's the question then. Let's suppose that I am at this point in the room, and suppose that I take off and start moving with that velocity right there. Notice that X, Y, and Z are all changing. Now we have a pretty weird question. If I want to just know how fast is the output, how fast is temperature changing, and I know from this given, I know how fast X is changing, but I also know how fast Y is changing. I also know how fast Z is changing. How do I compute the output change? I got 3 input changes. Do I multiply them or something? I mean, how does that work? Right? It's a non-trivial question, right? It's not immediately obvious. Single variable calculus isn't really very well set up for this. Said differently, how do I account for the fact that I'm going at some sort of an angle? It's not like there's just a t-axis and I'm moving along the t-axis, right? I'm moving in some random direction. How do you account for the angles? Not obvious. This is one of the things that we're going to learn in this class. This is a multivariable calculus problem. And so I'll make the observation, this is very real world. This is very three-dimensional world that we live in. And notice, I didn't have to get particularly obscure to identify an example where we have a multivariable function and we're taking a derivative kind of in some sense with respect to 3 different variables, right? Pretty easy example of where you need multivariable calculus. Okay. All right, related example. Let's suppose I have a lump. Right, we already kind of talked about this idea. And on this lump, let's suppose that the density is not constant. How do we compute the mass? Can't just multiply density times volume if the density isn't constant. And I know y'all have seen Calc 2 problems where you take slices in whatever appropriate direction. And if you do the slices and look at one slice at a time, you can, the way they have those questions set up, you can compute the total mass. Here's the thing. In those examples, the density is a function of one variable. Right? Here we're entertaining a scenario where the density depends on all 3 variables. So however I might slice it, I can't say, well, on the slice, the variable, the density is constant on each slice. No, it's not. The density depends on all 3 variables in some weird way. Calc 2 will not answer this question, right? It's a non-starter. So how are we going to address this? How are we going to compute the total mass? Again, the sticky wicket is that we have here a function of 3 variables, not 1. That's ultimately causing the problem, right? So this is a multivariable calculus problem. And what do we do? How do we deal with this? And good news, we have an answer, and it's going to work out just fine, right? But that is something we're going to need to talk about. Everybody on board? So what I like about these 2 examples is they're easily relatable. It shows that, look, multivariable calculus is not something that you need for only the most sophisticated of scenarios. Multivariable calculus is the solution to very simple, relatable kinds of questions, right? This is not obscure stuff. This is very common, very broad stuff. All right, now, slightly worried about the possibility of painting this as too simple. Let me show you some harder applications. Okay, so a lot of people think incorrectly that math is, it's pretty much for physicists and engineers, right? It's not true. Not true. If there's any econ majors in the crowd, maybe econ second majors or minors or whatever. Here is an application to economics that you can't do without multivariable calculus. Here are some letters of the alphabet that are commonly associated to economic variables like price and quantity, etc. Right? And by the way, I know very little about econ. Right? You're not about to learn any econ here. Right? But let's suppose we have an economic model, and I just made this equation up. This is just a placeholder to help me make a point. This is kind of what economic models look like. Very often, all exceptions, they're all different, of course. But very often, you don't know, P equals some function of other variables. Very often, it's just, there's various variables that contribute to various players that have to add up in some way, and all you know is that this expression is constant, or let's say 0. Right? So it's an equation, and all these variables relate by way of this equation, but I can't solve, for example, for P. Right? Okay, well, but still, even though I can't solve for P, I might still want to know how fast P will change under a certain set of conditions. In particular, let's suppose that I know how fast these other variables are changing. Maybe I have control over them. Maybe I can measure them. Whatever. So with the understanding that these variables are changing at some rates, how can I use the model to identify how fast P is changing? And well, this is a multivariable calculus problem. This is another thing that we're going to learn how to do in this class. We're not going to do it now, but we're going to do it. Is that cool? Everybody happy? Okay, so if you're an econ major, you're going to need multivariable calculus, and this is just one of many examples of how you'll need the multi. Okay, real quick side note. This comment that I made up here, that the world is three-dimensional, this is tip of the iceberg of why we need multivariable. We live in a three-dimensional world, depending on how much you believe about modern physics and 10 dimensions and all that stuff. I don't know. No comment on that. We live in an at least three-dimensional world, right? So what? Well, we represent spatial dimensions with spatial variables like x, y, z. Right? Those aren't the only variables that we have to deal with. Spatial dimensions are just not all we're interested in. Here is a nice, easy, no science fiction involved. This is not a movie about the fourth dimension or black holes or time travel. Nothing of that spooky stuff, right? This is just economics. And yet, check it out. We have 5 variables, all of which depend on time, and therefore arguably 6 variables to keep track of. And if you were to say, well, what dimensional space are we doing business in here? We're doing business in 6 dimensions. It's kind of creepy if you think about it, right? So anyway, what I like about this example, then, it shows that this idea that, well, we live in a 3-dimensional world and therefore we have no need for anything above 3-dimensional math. Nonsense. Obvious nonsense. Right? If you're going to do any economics, and by the way, let's suppose you're an engineer. Yeah, okay, it won't be these several variables, but if you're working on an engine, well, it's going to depend on temperature and pressure and the richness of the mixture and the various design features of your engine and blah, blah, blah. You could easily have 8 or 10 variables. in which case you need to be able to do math in 8 or 10 dimensions. Right? Okay. So we are not going to restrict ourselves to 3 dimensions here. The good news is we don't particularly need to. By the way, I'm not going to ask you to draw any pictures beyond 3 dimensions. Sigh of relief, right? Because you can't, and neither can I, and don't believe anyone who says they can. Right? That's not possible. We are confined. We are stuck, right, in this merely 3-dimensional world. So you can't draw the pictures, but you can do the math. And the good news is that if you have a good understanding in 3 dimensions, then like that geometric intuition that you'll have in 3 dimensions in most, not all, most cases will allow you to sort of extrapolate to, okay, how do I do this in higher dimensions? And we'll see examples of that coming up throughout the course. Okay, how we doing? Pausing again. Everybody buying what I'm selling? Okay. Scary stuff. A lot of y'all have probably seen these equations before. This is Maxwell's equations, a version of Maxwell's equations. Wow, a lot of intimidating notations, right? So what does that mean? It's something we're going to learn. What does this mean? It's weird to have a differential that's a vector. That's something we're going to learn about. It turns out it makes great sense. It's very natural. What does this construction together mean? It's another thing that we're going to learn. This is all multivariable calculus. Maxwell's equations are just straight up equations in the language of multivariable calculus, right? So if you're engineers, physicists, probably even chemists, I don't know enough about chemistry to really know, but I would kind of suspect. And therefore you need to understand electricity and magnetism. Well, you're going to be doing some multivariable calculus. Like so. Okay, so we're going to try to figure out what all these things mean. We're going to try to figure out what these expressions mean. What are the constructions that these expressions represent? Right? How does that work? We're going to also try to understand what is this statement saying and why is it true? Why should the left expression be equal to the right expression? It turns out there's very natural reasons for this. It all makes loads of sense if you look at it just the right way. So understanding multivariable calculus is going to give us a great insight into how Maxwell's equations work and why they, well, the why is, it gets a little philosophical at some point. Why are we here? Why does the universe work the way it does? But in some reasonable sense, why is it plausible that the physical world works the way it does is something that we're going to be able to get our hands on, which is cool. And then lastly, once we understand this, how will that help us to have some good intuition about, for example, electric fields? What do electric fields look like? How do they behave? And understanding these equations will help us with that, I think, significantly. Okay. So depending on your major, you may have to take an E&M course. I guess that's Physics 152 or something along those lines. If you've already taken that course, you probably recognize a lot of this stuff. If you have not already taken that course, good. Because then when you do, you will have a huge advantage. You'll understand all of the multivariable calculus that they're going to kind of sweep under the rug and, maybe broad stroke, special cases, keep it super simple. If you already have a good, full understanding, you just have an unfair advantage over everybody else. So, hope that'll be useful. Okay. For the chemistry major out there, you have to understand molecular bonds. What makes molecular bonds work? Well, it depends on how electrons behave. What governs how electrons behave? Schrodinger's equation. I probably didn't pronounce that right. So, okay, deep down underneath it all, this is what makes chemistry work in some sense, right? So what's going on here? What is all this nonsense? Well, that's not what we're going to talk about in this course. This is a partial differential equation. It's not what we're going to do here. But I just like to point out that object. This is the Laplace operator, and this is an object of multivariable calculus that we will be talking about quite a bit. Okay. All right. Okay, so anyway, my point here is to try to persuade you that multivariable calculus is useful, not only at the obvious low levels, but also at the sophisticated high levels. Multivariable calculus is just all over the place, and this is my little pithy summary of all this. I think it's fair to say multivariable calculus is the calculus of the real world. Right? Single variable calculus is this narrow special case that is useful in simplified models and things like that. But when you actually have nitty gritty, real world, ugly problems, usually they're multivariable calculus problems. That's why we're here. That's why your major requires that you take this course. Does that seem reasonable? Okay, pausing again. Everybody's good. Okay, so let's move it along. The very first thing I'm going to say in section 1.1 is I want to talk about this little header here. So I've got this gray shaded box around most or all of this page. This is going to show up in various places in the notes, and it's because of edge cases of a difficult question that I have to deal with. I talked about this some in the recording that y'all have all listened to. During lectures, I have to make a bunch of difficult, kind of painful decisions as to what am I going to talk about, what's worth talking, what's worth the precious class time, that I have to work with, right? And such hard choices, right? So some things y'all can read. I know you can look at certain examples and you can follow the algebra. You don't need me to help you with that kind of thing. Some things are sophisticated and challenging and geometric, and really benefits from me being able to talk through and point and hand wave and stuff like that. Well, there are these edge cases that are kind of borderline, like I feel like it needs to get, I really wish I could talk about it, and I want to be able to contribute towards y'all's learning of these things, but I just can't quite justify the very little class time that I have. And so what I have done in those cases is, I leave that stuff in the notes, but so you can have this as a reference, but we just don't have time to actually talk about it. So when you see something like this, just keep in mind it is something that I wanted to help y'all with a little bit, and that's why these discussions are here. But you do have to read it on your own. Okay. All right. So usually in such cases, I will still have a little something I want to say. I like to talk about this point. This is just a notational thing, but I think it's a pretty easy little notational conversation. I would rather refer to that vector like so, as opposed to that. I'm crossing it out not because it's wrong. It's perfectly fine. It's very broadly used notation, but I just don't like it. So I want to explain why. I think y'all know that points and vectors are kind of related to each other. They're not exactly the same thing, but they're easily relatable. And so, for example, this point, P1, I can think of as a vector, like so, that I can also call P1. Right? And you give me any point, I can make such a vector. You give me any vector represented with an arrow with tail at the origin, I can interpret as a point. So notice if you represent P1 as a vector like that, and if you represent P2 as a vector like this, notice this notation makes sense because literally when you add P1 to that green vector, you get P2, right? So very natural and I think highly advantageous. Now, why? Why do I think this is such a great notation? Why do I prefer this as opposed to this? And the answer is algebra is a good thing. Algebra is our friend. Algebra is the foot in the door that allows us to solve problems very often. I like algebra. I want to see it. Algebra is an opportunity. I don't want to conceal, hide opportunities. Right? So I think this is sort of it's just a missed opportunity. Why would I conceal the good thing? I think this, by exhibiting explicitly that minus sign, I think this is a more useful notation for your consideration. And then lastly, real quick, very often we need to represent vectors like this, x comma y, comma z, whatever. We're going to use this notation here. We're going to call it R vector. It's pretty standard, certainly very common. There are some downsides to that notational choice. We're not prepared to talk about those downsides just yet, but there's something a little unfortunate about it. So in earlier years, as of maybe a year or more ago, and for all the way back, I used the x vector because it bypasses what I think are some downsides of calling it R vector. So if you look back at my old exams, for example, these vectors will be called the x vector. And so if you look back at my old exams and you see x vector, okay, it just means this, that's all. Right? It means what we are now, going forward, going to call R. Okay. All right. So by the way, we have finished section 1.1 now, by which I mean I've said all I'm going to say about 1.1. There is other stuff in the book. Make sure you read all of that. Reminder, you're responsible for everything that's in the book, as well as what we talk about in the lectures, as well as what's in the notes that we don't talk about, etc. So on to 1.2. I want to talk about this thing called a parameterization. Ultimately, a parameterization is a function. It's a particular kind of function. It's a really useful kind of a function. In particular, it gives position, I should say rectangular coordinate position. We'll talk about other coordinate systems later, but the word parameterization always means rectangular coordinates of position thought of as functions of a single parameter, which in practice, very often we like to think of as time, and so we call it t. So I claim y'all have seen something like this previously in your Calc 1 courses. You probably did some questions where, Bob's in a car and he's driving along the road and his velocity in terms of time is such and such. Find his position at a certain time, or find his position as a function of time. Parameterization, right? They don't use that word usually, but ultimately that's what they were talking about. So we're opening it up now to the possibility that we might be parameterizing with multiple coordinates. So maybe position in space or position in the plane. Multiple position coordinates, all as functions of time. Is that cool? All right. Okay, so some easy examples. Here is a parameterization. Notice we have literally position, x and y, r vector, right? That's position as a function of time. That is x and y themselves are both functions of time. So there you go. That's a parameterization. And specifically, x is that function of time, and y is that function of time. Okay, so altogether, what does this look like? What is the curve that this parameterizes? Say it differently. Okay, well, I am going to notice, kind of conveniently, check it out, that, well, x being cosine t, if I were to put that right there, and y being sine t, if I were to put that right there, I mean, I remember my trig, right? And trig tells me that cosine squared plus sine squared is 1. Well, that means that because that's what x and y are, that parameterization, every point that it produces is on the unit circle. Is that cool? Everybody buy it? We got lucky. We just happened to have a pre-existing awesome relationship between these two functions. Right? Don't count on that. You won't always get that lucky, right? Where oh yeah, yeah, right, sweet. Right? That's not always going to happen. But when it does, when the fish just jumped in the boat, good thing. Okay. Pause on this one. Is everybody happy with that? Okay. Let's see here. Here's another one. Here is a parameterization. What is that? Now let's confess we don't notice any immediate, identities relating those two coordinate variables. By the way, easy to lose track, but don't forget that's x and that's y. Right? Notice I didn't explicitly say so. Right? Very often parameterizations just be written like I did there, and of course it's implicit. First coordinate, second coordinate, right? That's all pretty standard. But you have to kind of consciously think to yourself to remind yourself that that's what's happening. Okay. All right, so here's what I'm going to do. The way I'm going to understand this parameterization, two-step process, I'm going to first solve for that t. If t minus 1 is what x is, then I can solve for t. T is x plus 1. So solve for t in one of the equations, and then plug that in the other equation. Solve for t in one equation, plug it into the other equation. That's all it is. And you can see that second equation says y is 3t plus 4. That's what this says. Y is 3t plus 4. Plug in that formula for t. Boom. And so our punchline from that process is that this curve, every point on that curve is on that line. Everybody see how I did that? It's a cool trick. Happened to work in that case. By the way, here's another thing we could have done. Sometimes the following works. Keeping in mind this is what x is, and this is what y is. And you notice that the expression we have for x and the expression we have for y, they look kind of alike. I see a relationship between those expressions. I mean, they're both polynomials. They're both degree 1 polynomials. Well, they have a lot in common. And when expressions have a lot in common, it's not rare for you to be able to perform algebraic operations on one to turn it into the other. And if you just think of that as a sequence of operations to do to that green equation, right, do that to, well, you got to do it to both sides of the equation, then notice what you end up with is a relationship between x and y. And notice it's the exact same relationship between x and y that we got using that first method. Well, that's kind of cool. What do you think? Okay, so I showed you 3 different methods so far for how to identify, right? So there's the notice the convenient relationship method. Keep your eyes open for that. Sometimes life is good. Sometimes it just falls in your lap. Sometimes you can do this thing where you solve for t in one equation and plug it into the other. That works sometimes. And then sometimes you can do this thing where you kind of manipulate one expression to turn it into the other. 3 different methods. Why did I show you 3 methods for solving the same kinds of questions? And the answer is that none of these methods will always work. Obviously, you don't always just notice an awesome relationship. For the second one, sometimes you can't solve for t. What if this expression wasn't a degree 1 polynomial? What if it was a degree 3 polynomial? You can't solve for t. Okay, and then this third one, what if these relationships just don't look enough alike and there is there's no little algebraic little trickery like this that you can do where it just doesn't, if you can't see how to turn one expression into the other, then this expression fails. Or this method fails. So all of these methods are, well, sometimes, right? They solve some kinds of examples of these kinds of problems. So a metaphor that I'm going to be using a lot in this class is the idea of each one of these you can think of as a tool, and I'm showing you multiple tools for this category of question that you should put into your mental toolbox, right? These are tools for your toolbox, and you're going to hear me say that a lot throughout this course. Point being, don't think of these as pick your favorite and rehearse it. That's not going to do it, right? If you only know one of these and you've gotten real good at that one method, but you don't like the other 2, well, the other 2 are going to be really useful in different circumstances. So make sure to get good at all of these methods. And then furthermore, make sure that you kind of, strategize. What should I be on the lookout for? What kinds of parameterizations should make me want to do this method? And what earmarks, what signs should I be on the lookout for to do this method or what have you? Right? And try to get a good sense for when should I use a screwdriver, when should I use a hammer, when should I use a socket set? Right? All right. Okay, here's a harder one. This is a parameterization of a curve in 3 dimensions, because you can tell we have an x, we have a y, and we have a z. Okay. Can I try to find an equation that will relate these and maybe kind of rip off one of the previous methods? No, it's not going to work. An equation we're going to see later, but I'm going to propose now, and I think this is believable. If you have an equation in 3 dimensions, it gives you a surface, not a curve. We kind of know this is tracing out a curve. Position as a function of time. It does like this. It's just literally drawing out a curve. So there's a mismatch. There's no way that I can use what describes a surface to describe a curve. So it's not going to happen. So we need some different method. Now, again, tools for your toolbox. This won't always work. When it does, it's very handy. Notice, in some sense, we kind of already understand this part. Right? By the way, this is a good one to memorize. This whole cosine t, sine t thing, right, comes up a lot. Very useful tool. We know that's a circle. Now let's just think geometrically. I'm looking at points in 3 dimensions, but I want to just think about just the x and the y. What does that look like geometrically if I just kind of ignore z, pretend z isn't there? And one way to think about this is that it's describing the projection, sort of the shadow, into the xy plane, right? If you have some point and you say, let's forget about that whole z thing, right? Well, then you're just going to look at the point in the xy plane, sort of, if you will, straight below it. Is that cool? Okay, well, so apparently, whatever this curve is, its shadow in the xy plane is kind of going around in a circle like that. We've already studied cosine, sine. So the I don't know what this curve is doing, but the shadow is going around like this in a circle. And then you look at the other part. This is pretty easy to understand that, the z coordinate is just t. How do I understand that relationship? Well, as time passes, the z coordinate being t, the z coordinate increases also. Said differently, it just goes up. Is that cool? Is everybody? Yeah. Okay, so between the two of these observations, if you think about it, kind of combine these together, and by the way, we're going to make heavy use in this class of geometric visualization, just kind of seeing things, using your geometric intuition. There's kind of no way around it, right? So if you're not good at visualizing in 3 dimensions, then this is something you want to consciously practice, right? Try to force yourself into being able to get better at this, because it's unavoidably helpful. This is a nice example. If you have a curve and the shadow is doing this, and the z-coordinate is doing that, kind of put it together, and you can persuade yourself that this parameterization is doing like so. This is what we call a helix, kind of like a spring. What do you think? Now again, tools for your toolbox. I wouldn't go so far as to say that this comes up enough that you should memorize it, but it will come up again in this course a couple times. So yeah, you probably should at least kind of be aware of that. This idea of looking at different sort of coordinate parts, if you will, is pretty useful. Okay. Next. Let's turn it around. The examples we've done previously, I gave you the parameterization, and the question is, what does the curve look like? We're going to turn that around backwards. Now I'm going to say, suppose I know other information about the curve. How do I create the parameterization? I think this is really important. When I was doing math and physics and stuff when I was y'all's age, I had to create my own parameterizations. Most real-life scenarios will not come with your curve pre-parameterized for you, right? You're going to have to create your own parameterizations. So I'm going to show you my favorite method for parameterizing. When you have a graph, we'll talk more about what graphs are later, but if one of the variables is solved for in the equation, this is what we call a graph. You might say one of the variables is a function of the other variable. If you have a graph, here's the big trick. The graph parameterization. Just let t be the input variable. In this case, our input variable is x. That's the big trick. That's all it is. Let t be the input variable. You'd be amazed how well this works. Super powerful. Easy example. Check it out with this this equation right here. It is, in fact, a graph. One of the variables is a function of the other. Sweet. The input variable is x. I'm going to do as instructed. Let t be the input variable. Okie dokie. Well, x is my input variable, so I'm going to let x equal to t. I claim that it's all over but the shouting at this point. There's nothing I can do to make this not work. In particular, because I've made this choice that x is equal to t, well, I kind of have to let y be t squared, don't I? Done. We win. Victory. We have position as a function of time. So it's a super powerful trick. Nice and simple. This will instantly parameterize lots of kinds of curves. Here's one. By the way, this one I don't even have written as a graph, but I can rewrite it as a graph by solving for x. Right? Now I've got a graph. One of the variables, in this case x, is a function of the others. The other, singular. And now it's same deal. My input variable is now y. So let t be the input variable y. And then again, I have no choice but to let x be this. And again, victory, we have position as a function of t. I think that's kind of sweet. I don't even know what this curve looks like off the top of my head. Right? I can parameterize it though, even though I have no sense for what this looks like. Cool trick. Real quick, last example. This is basically the same thing, but using polar coordinates. All you have to do with polar coordinates, by the way, if you haven't seen polar coordinates before, we'll talk about this later, but the big idea is it's this geometry right here. It's just kind of representing location by an angle and a, air quotes, distance per this picture, which I think pretty easy to motivate this right here. And just plug in. So here I have r as a function of theta. Plug it in there, like so. And again, victory. Position as a function of a single parameter. And if you want to rename theta and call it t, suit yourself. You don't have to, but something kind of satisfying. But there's also something kind of nice, by the way, about if you leave it as theta, then that gives you the advantage of your parameter actually meaning something geometric, right? And that can be handy too. So it's a pro-con as to whether you rewrite this theta as t. All right, is everybody good? We seem to be out of time, so we'll draw the line right here. Nice to meet y'all. See you on Wednesday. Have a good one.